We proceed with the next presentation by Zheng Mao Yang. He will be talking about evolution and characterization of thermal shock damage in oxide-oxide ceramic matrix composites.
Okay, thank you, Mr. Chairman. Now you see the title of my work again. We're going to talk about so-called ceramic matrix composite. And the loading, what you're talking is actually thermal shock induced damage in the material. Good. My name is Yuan. I'm from Tsinghua University, and Mao Yang's my PhD student. Good. A few words about my talk, short introduction, background of the work, and the experiments, and then modeling and conclusions. Good. A few words about application. CMC, the so-called ceramic matrix composite, becomes very interesting just due to a major application of the aero engine industry. The reasons actually, you see here the temperature, down in cabin, of course, and temperature in the combined inlet. You see, we are actually the temperature, inlet temperature to combined exceed 200 degrees C. That means the conventional nickel-based alloy becomes more and more difficult for higher temperature. And actually, the third generation of nickel-based alloy single crystal can working only up to 1,100 degrees C, not higher. Therefore, the cooling is a huge problem. Therefore, if you want to introduce induced higher efficiency to reduce the emission, then you have to increase the temperature further and to increase efficiency. Therefore, we need actually now new material. CMC becomes very interesting. The reason is actually the application temperature of material is exceeded 1,000 degrees C, actually up to 1,400 degrees C. This is the limit temperature which we can use for long life. Okay, that's a group, the reason for its work. Okay, the ceramic matrix composite materials actually now under testing in different demonstrators. For instance, you see here that is like a combustor will be used as a stators, and there's also a pure demonstrator for as turbine and so on. There are very big problems actually. This material is rather new, not only for the material designer, but also for structure designer actually. That means we are actually not familiar with the material's property. We have much significantly lower heat conductivity in material. That means that if you have varying temperature, you will have higher thermal stress. That becomes a problem. You see, in aero engine, we are working, generally speaking, under transient temperature condition. That means the temperature material in our engine changes always as a function of speed and maneuver and so on in that case. Therefore, we always talking about so-called transient temperature situation. If the heat conductivity is lower, that means the temperature variation results immediately to the high stress. Therefore, the thermal shock becomes a huge problem for such material. Okay, we are going to talk about so-called thermomechanical fatigue. That means the fatigue in such material is all coupled with temperature and with temperature gradient. Materials damage mechanism of material at different thermomechanical loading is actually not so understood right now. Representation of damage is a point has to be investigated and so on. More point of such as damage tolerance assessment method and so on. There are environmental effects and so additional problems and so on. There's many problems which has to be studied. In the present talk, we are just talking about limit ourselves to these problems. We're going to talking about sudden change in temperature and to study the effect of the temperature to the material safety, material damage, and so on. Okay, and finally, we're going to talk about material damage, the representation of damage, and so on. Good. we manufactured this kind of specimen. That is, we use a special ceramic matrix material that is so-called oxide. That means the fiber is oxide and this matrix also oxide material. And this material is actually where we used for lower temperature up to 1,200 degrees C actually. Therefore, we're going to test those up to the temperature. Okay, the materials are rather porous. We have usually a lot of, due to the manufacturing technology, the porosity is not available actually in this material. So even hoped to induce such porosities in the material. Okay, the specimen is actually in this the size of it. The thickness of the specimen is up to, I would say, 2.8 millimeter thickness, and the specimen is actually manufactured with a water jet, and therefore the surface of cutting plane of the material is rather good, what to say. And okay, you see this kind of large scale voids here is just due to pour out in cutting. Actually, that's not the point. Anyway, that the cutting plane we see it's rather clean, and you do not see in cracks on the surface. But you have on the free surface you have such kind of surface crack on the surface. That is actually you see that's just due to cooling process in manufacturing. Okay. That's actually the in plane. That's out of plane actually, if you want. That is, as I said, this is thickness. The thickness of the specimen is 2.8 millimeter. That is actually the specimen. Okay, and we're going to test this material. That means the specimen will be put into the oven and heated up to 1,000 or 1,000 or more, and then keep 10 minutes for homogenized temperature. And then take it out, put into water to quench process to introduce the higher. Of course, very high temperature shock, of course. You can cool it also in air. And okay, you will see also such similar effects due to temperature shock, but of course it's not so high as in water. We want to quantify the effect, therefore the first we tested actually in very high temperature gradient. Okay, that is the procedure. The holding time, that is the control curve, heat up to 1,000 degrees, something like that, I think, or more. We tested from 400 up to 1,200 degrees C, and then cool down. That is actually temperature we measured. You can measure temperature, of course, use the thermocouple or thermal element, or you can use also the infrared method. You see the difference between the green symbol show you the measure value by the thermocouple, and the blue point show you the measure value of used infrared equipment. You have small discrepancy between them, just due to in high temperature you have actually effect of environmental actually in the case. In that case, it's actually you see agreement between two different methods is rather good. Okay, of course, good. And then we see what happening in material after thermal shock. You see after one shock, actually that means after one water quench, you see cracks actually not only in the plane, that is actually the so-called delamination between the fiber to the matrix, but also you see the cracks in the matrix actually. Now, it's a point, of course, how to quantify the damage in the material. We see a lot of contributions about in micromechanics trying to, as I heard from first talk, they want to quantify, describe the process after lamination. But the point is actually this material will be designed exactly in reinforced direction is a loading direction. That means the lamination and the tension is not a problem. That is loading direction. You see the cracks. But the load will be carried by fiber only under tension condition. Okay, compression situation, shearing is different situation usually. But in our case, we're going to measure this damage phenomenologically. Just use the micromechanics procedure. Okay, after four quenches or 8 quenches, you see much more micro cracks, mainly now in this direction. this crack remains as one. That is exactly the same place we photographed. And you see the much more cracks actually in this distribution. Okay, I want to actually, how to quantify the cracks or crack density is of course a problem. But we want to, as I said, just measure the stiffness of the material to quantify the damage evolution. Okay, if you look into the material, we take different computer X-ray, computer topography, to see within the material. We can see this kind of, that is the pros, initial pros. What for us interesting actually, this kind of lines, they are cracks. But also that means what we saw in last slides, we see the crack on the surface. Within the material, you see also similar situation. That means if we're talking about damage, the size of specimens, of course, a point here. Okay, that is actually after four quenches actually, and you see the initial porosity is very high, but you see macro cracks just induced due to the quench. Okay, then we use actually the conventional damage definition. That means the reduction of the Young's modulus defined as damage. Then you see this correlation. That is, here you see the elasticity modulus. So we can measure the elasticity modulus after quenching. And then that is the temperature, quench temperature. You see this kind of distribution of it. That is the 1,000, that's the temperature, of course. That means room temperature up to 1,200 degrees C. You see this kind of distribution. That's of our material. And this other material, actually, in similar material. You have that means what for us interesting is actually, we have this kind of the correlation between reduction of material stiffness as a function of quench temperature. That means if the temperature is lower than 400 degrees C, the material will be independent of thermal shocking. Beyond that, you see a rather strong the reduction from 100 to 128 up to 100, around about 100. That after that, the thickness, this shock becomes also more or less constant. Independent temperature. Okay, of course, this material will be used up to 1,000 degrees, 1,200 degrees only, not higher. Okay, anyway, this is like a phenomenological set as after one quench. If you repeat it, of course, the situation will be different. Okay, we said, okay, that this distribution can be empirically fitted by this function form. Okay, there's something you can remember, something similar to temperature, transient temperature behavior in metal, in similar form, right? Okay, anyway, if we said, okay, we're going to try to describe this behavior, Young's modulus as a function of the loading quench cycles. That means we quench one time, and after that repeated. That is actually cyclic thermal loading. Okay, actually, if you want, you see, okay, that you can find this correlation. That means we have different quench temperature. That is the 1,200 degrees C, 1,100 degrees C, and 800 degrees C. 400 will remain constant. That is actually not changed. You see this such correlation. Okay, that is empirical. You can find this correlation between number of shocking and to Young's modulus. The point, of course, how to quantify the correlation. Okay, good. Okay, accelerate. Now, you define D in this form, and you found, okay, you can introduce this form. The point is actually, we said we were at this form. That is shock temperature. The reason, actually, that's correlation again. And the reason, actually, we can use this kind of simple model to correct the relation between stress to shock temperature. That is actually simple one-dimensional solution from materials mechanics. And if you use that, okay, T is actually linear correlated with stress. Okay, then you say, okay, well, I used damage mechanics, said, okay, we defined elastic strain energy density as a function, as driving force. Then we said, okay, you can create the correlation, find, okay, can build this relation. That means that is our damage evolution equation for force shock. You can do more. That means you can introduce, okay, well, I'm going to say, okay, I let Y change with shocking. Of course, after one shocking, the Young's modulus decreases. That means this Y will be smaller but the same temperature. That means y here is not constant. It's a function of d. And then if you substitute into it, integrate this equation, you find this correlation more. That means that's a fitting. Okay, that is actually the correlation between delta d I is the number of shocking, and then the function of this form. Okay, and you can use this fitting to identify the parameters, and finally you see this correlation. That is the d. That is the pi. Pi is defined as actually the reduction of elastic strain energy after nth shocking. Good. That is actually a continuous function of loading, actually mechanical loading. Okay, I conclude. That means in our study we learned that thermal shock damage in CMC is dominated by matrix cracking and fiber delamination, which can be represented by reduction of Young's modulus. That means so we just consider the in plane, of course. The phenomenological damage model is introduced in the case. We said, okay, that this model can be integrated actually directly into the continuum mechanics. The cyclic thermal shock increases material damage driven by the current elastic strain energy density, and the damage approaches the saturated activity cycle is going to be reach the final value. A damage evolution model establishes the case. Thank you for your attention.
Thank you.
We have to come for a question.
No, that will be in the end.
Okay, good.
So don't go away.